Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss Fraunhofer diffraction at N-slits, that is multiple slits. Let's begin. Let a parallel beam of monochromatic light having wavelength lambda, wavelength of monochromatic light is incident on n parallel slits. Each slit having the width a, the width of each slit, capital N with the number of slits. The slits are named as S1, S2, S3, S4 up to Sn, n number of slits, each slit having the width a. The parallel rays are incident on these slits a be the width of each slit, that is the distance, and small b separated distance between each slit. So, here is the distance b. So, a plus b, the total distance is the a plus b. So, a plus b, which is known as the grating element, a the width of the slit, b is the distance of that opaque portion. So, the distance between these two slits, which is a plus b, known as the grating element. In the Fraunhofer type diffraction, the source is at infinity from that of slit, and again the screen also is at infinity from that of slit. We use a convex lens L. The parallel rays After diffraction, focused at point O at point O, we have the central bright or the principal maxima is at point O. The intensity is maximum at point O. If it is refracted at an angle theta, again the rays are refracted. I just some of the basic rays at an angle theta. After diffraction, they focus at point P. You have to observe what be the intensity at point P, the condition for maximum or minimum. We know from single slit diffraction the amplitude of the wave that are from these slits having a amplitude of the wave is a sin alpha by alpha, where a any constant and alpha is equal to pi a sin theta divided by lambda. That from single slit diffraction we know the amplitude of each wave from that of secondary wavelet. Now, let me draw a perpendicular from the slit S1 to these slits named as, these are the perpendiculars named as, let N1, let N2, N3, so on. Here N, N minus 1, these are the perpendiculars. So, the path difference between the rays from S1 and S2, the path difference, here the path difference between the rays S1 and S2, the rays from the slit S1 and S2 is the path difference, let S2 N1, S2 N1, which is A plus B, that angle is theta. So, A plus B sin theta, A plus B sin theta. Therefore, corresponding phase difference. Therefore, corresponding phase difference is equal to 2 pi by lambda into path difference. That is 2 pi by lambda path difference a plus b sin theta. Let that one be 2 beta, say. Therefore, the successive phase difference between the rays 2 beta, here again 2 beta, that is 4 beta, again 2 beta, that is 6 beta, like that of the phase differs successively. Therefore, the phase difference between the waves from S1 and S2, similarly S1 and S3, S1 and S4 becomes the phase difference like 2 beta, 4 beta, 6 beta, and so on. Gradually, successively, phase differs. The waves starting from that of slit S1 like up to Sn. Thus, the resultant of n number of amplitudes is given by each having amplitude a sin alpha by alpha, a sin alpha by alpha, and having phase difference successively, phase difference successively by a constant of 2 beta, 4 beta, 6 beta up to, which will provide a maximum or minimum at point P. On that basis, the maximum and minimum can be obtained at point P. So, using the vector calculus, therefore, using the vector sum method, there are n number of vectors having amplitude a sin alpha by alpha, each of phase difference 2 beta, 4 beta, and 6 beta. So, the vectors, let that is a sin alpha by alpha, again a vector a sin alpha by alpha, again a vector a sin alpha by alpha, up to so on n number of vectors. So, the resultant is calculated. Here the angle 2 beta, here the angle 4 beta, here the angle 6 beta, and so on. For nth number of terms, the angle will be n beta. In this way, the resultant can be calculated using vector sum method. The resultant amplitude the resultant amplitude at point P. R is equal to individual amplitude A sin alpha by alpha. We use the formula for n number of waves having the same amplitude. So, use n number of harmonic waves concept. So, that can be sin n beta divided by sin beta. That term is derived from this vector sum. Therefore, the resultant intensity at point P, we know the relation between amplitude and intensity, that is k r square, where k is the proportionality constant and its value is equal to 1. Therefore, we have I is equal to r square. As we know, I directly proportional to r square, intensity is directly proportional to the square of the amplitude. Now, we put the values. So, the values here, k not equal to 1, we have k r square, or I is equal to values of r is put it. So, a square sin square alpha by alpha square into sin square n beta divided by sin square beta. If we take k a square, if k into a square is equal to I naught, that is the maximum intensity, maximum value of I, we have I is equal to I naught sin square alpha by alpha square into sin square n beta divided by sin square beta. That will be the expression for resultant intensity. From that of expression, let us see equation number 1. That term sin square alpha by alpha square, that term basically denotes the diffraction. We know that with the diffraction due to the single slit that expresses, and the term sin square n beta by sin square beta, that represents for interference. Due to n number of parallel slits, we obtain the diffraction pattern on screen due to both diffraction as well as interference. From that of equation, it clarifies sin square alpha by alpha square express the diffraction pattern due to single slit, as you know, and the second factor that express the interference pattern due to n number of slits. We can easily find out the expression for intensity in case of single slit and double slit from that particular expression. Look how we calculated that one. So, I use it for n is equal to 1. For n is equal to 1, sin square n beta is equal to sin square beta. Therefore, I is equal to I naught sin square alpha by alpha square, which is the intensity distribution, this is the intensity distribution due to a single slit. Next, for let me prefer n is equal to 2. For n is equal to 2, sin square n beta is equal to sin square 2 beta, that can be written as sin 2 beta square sin of 2 beta, which is equal to 2 sin a into cos a. So, 4 sin square beta into cos square beta. Therefore, intensity I is equal to I naught sin square alpha by alpha square into 4 cos square beta, or I is equal to 4 I naught sin square alpha divided by alpha square into cos square beta. So, that be the expression for intensity due to double slit. This is the intensity due to double slit. That is the expression for intensity due to single slit, that is the intensity due to double slit. In this way, that master intensity equation we can easily get by putting the value of n is equal to 1 or n is equal to 2 and so on. The intensity is calculated. Due to that particular expression, the diffraction and interference. In diffraction, we have principal maxima, secondary maxima and secondary minimas. What be the values of the principal maximas, secondary maximas and minimas? What be the conditions? Later we have to calculate it, that one from that intensity distribution equation. First one, for principal maximum. Principal maxima. When if sin beta is equal to 0, then beta is equal to plus minus n pi, where n from 0, 1, 2, 3 like that. Therefore, we say sin of n beta is equal to sin plus minus value of beta n pi, which is equal to 0. As say the product of two integer, therefore n that is the product of two integer which is also an integer. Therefore, we write sin n beta by sin beta is equal to 0 by 0 form. Sin n beta is equal to 0, sin beta is equal to 0. So, 0 by 0 form, which is indeterminate. So, sin n beta by sin beta, that value can't be evaluated directly. So, it can't be evaluated directly, but it can be evaluated by finding its limit as beta tends to plus minus n pi. its value can be evaluated, easily evaluated by finding limit as beta tends to plus minus n pi by method of differentiating differentiating the numerator and denominator How we have to evaluate that term? So, that term can be evaluated taking as limit beta tends to plus minus n pi sin n beta divided by sin beta, which is equal to limit evaluation beta tends to plus minus n pi, its differentiation d by d beta of sin n beta divided by d by d beta of sin beta, which is equal to limit beta tends to plus minus n pi, its differentiation n cos n beta divided by cos beta, differentiation of sin beta. Now, evaluating that limit, putting n pi in place of beta. So, n cos n plus minus n pi divided by cos plus minus n pi. So, its value will be plus minus n. Now, the equation for intensity. Therefore, intensity equation, therefore, I is equal to I naught sin square alpha by alpha square, that evaluating value. So, I is equal to I naught sin square alpha by alpha square plus minus n whole square, as you evaluating sin n beta by sin beta, or intensity I is equal to I naught n square sin square alpha by alpha square. That equation this equation represents the maximum intensity, and that maximum intensity is called the principal maxima. That maximum intensity is called the principal maxima. So, the principal maxima can be obtained, as we discussed at beta is equal to plus minus n pi. So, the condition for principal maxima is termed as beta is equal plus minus n pi, or the value of beta as we substituted two pi by lambda plus a plus b sin theta is equal to 2 beta. So, beta is equal to pi by lambda a plus b sin theta. So, the value of beta is pi by lambda a plus b sin theta is equal to plus minus n pi, or a plus b sin theta is equal to pi by cancel out plus minus n lambda, where n from 0, 1, 2, 3 dot dot dot. That will be the condition for principal maxima. When path difference is integral multiple of lambda. For n is equal to 0, that is the 0 order maximum. For n is equal to 1, 2, 3, we get first, second and third principal maxima. The plus and minus sign basically indicate that there are two principal maxima for each order on either side. Look at that particular expression. That particular expression does not contain capital N. Capital N as you take the number of slits. So, for principal maxima there is no importance of the number of slits, or we can say that with the grating element. The position of a principal maxima are independent of the number of slits for a given grating element a plus b, the width of each slits and the distance between two consecutive slits, which is the grating element a plus b. Now, the condition for that with the principal maxima, the condition for principal maxima we obtained. Then secondary minima, then for minima, how minima is obtained. So, the intensity at a point due to n number of slits will be minimum when the term sin n beta is equal to 0, but at that of case sin beta does not equal to 0. If sin beta will be 0, then we have the maximum intensity. That is the only reason sin beta does not equal to 0 to get minimum. Therefore, n beta is equal to plus minus m pi, where m is equal to the values except 0, n, 2n, 3n, etc. Because for these values of m make sin beta is equal to 0. Therefore, except these values, another values of m is considered here. Then the term sin n beta divided by sin beta, which is equal to 0. Therefore, intensity I is equal to 0. That is the minimum intensity, which is the minimum intensity. Now, the condition for minima can be calculated. N beta is equal to plus minus m pi. Therefore, beta is equal to plus minus m pi divided by n, or the value of beta pi by lambda a plus b sin theta is equal to plus minus m pi by n, or a plus b sin theta is equal to plus minus m lambda by n. Here this one with the condition for minima, when the path difference is multiple of m by n into lambda. It is clear that for m is equal to 1, 2, 3 up to n minus 1, we get minima. From this equation, it is clear that for m is equal to 1, 2, 3 up to n minus 1, we get minima. When m is equal to n, again we get a maximum as explained above. As m is equal to n, we have the maximum intensity. Thus we say there are n minus 1 minimas, between two consecutive principal maxima. Since for small m is equal to 0 and m is equal to n, these two cases give the principal maxima, Therefore, n minus 1 minimas are obtained in between two consecutive maximas. These two are the condition for this one be the principal maxima, that one be the minima. Next, the condition for secondary maxima. Secondary maxima can easily obtained. So, the condition for secondary maxima. As there must be secondary maximum between two minima and there are n minus 1 minima between the two consecutive principal maxima. We have n minus 1 minimas. Therefore, there must be n minus 2 secondary maxima between the two principal maxima. In between two principal maxima, we have n minus 2 secondary maxima. So, the positions of these secondary maxima can be found. We have to differentiate the intensity with respect to the phase difference. So, the positions can be calculated by differentiating the position of secondary maximas can be found by differentiating the intensity with respect to beta. We get with respect to beta and equate it and equating it to 0, gradually it decreases. So, d I by d beta is equal to 0, or d by d beta of intensity I naught sin square alpha by alpha square sin square n beta divided by sin square beta is equal to 0. The constant term to that of outside I naught sin square alpha by alpha square d by d beta sin square n beta divided by sin beta square is equal to 0. Now, its differentiation, or I naught sin square alpha by alpha square, its differentiation as 2 sin n beta divided by sin beta. That differentiation sin square n beta by sin beta in form of numerator and denominator form, we have n sin beta cos n beta minus sin n beta into cos beta divided by sin square beta. Here is sin square beta is equal to 0. Look at that particular expression. Here these terms not equal to 0. Therefore, that term is equal to 0. So, we have again that is multiplied with this, we have that entire term will be equal to 0, or n sin beta cos n beta minus sin n beta cos beta is equal to 0. Here we take alpha as constant. Here we considering alpha is equal to constant. That negative to this side, n sin beta cos n beta is equal to sin n beta cos beta, or n sin beta divided by cos beta is equal to sin n beta divided by cos n beta, sin beta by cos beta, tan beta. So, n tan beta is equal to tan n beta. Let us prefer a equation number, let equation number 2. Now, we have to evaluate sin square n beta by sin square beta term. For evaluating sin square n beta by sin square beta, we use the triangle as here we use the triangle, right angle triangle having the angle n beta, that side as unity, that is n tan beta. So its hypotenuse 1 plus, according to Pythagoras theorem, 1 plus n square tan square beta under root tan square beta under root. So sin n beta is equal to sin of this angle is equal to n tan beta divided by 1 plus n square tan square beta under root. Now sin square n beta by sin square beta can be evaluated. Therefore sin square n beta divided by sin square beta, sin square n beta value n tan beta divided by 1 plus n square tan square beta under root into its square, so under root square into sin square beta. Here we have n square here n square tan square beta as the square, n square tan square beta divided by under root square, we have 1 plus n square tan square beta into sin square beta. Tan square beta is equal to sin square beta by cos square beta, 1 sin square beta 1 sin square beta cancelled out. We write it as n square here sin by cos, sin square by cos square beta, so cos sin cancel out, we have n square tan square beta, sorry tan is totally replaced, right, 1 plus n square tan square beta into cos square beta. So that is sin by cos, sin cancel out, so cos term exists, have n square divided by cos square beta is multiplied plus n square, again sin square by cos square into cos square beta, cos square cancel out, we have sin square beta is equal to n square divided by, let I use cos square beta plus sin square beta plus n square sin square beta minus sin square beta. I just add and subtract sin square beta, cos square beta plus sin square beta is equal to 1, therefore n square divided by 1 plus here n square sin square beta minus sin square beta is equal to n square 1 plus sin square beta is common, have n square minus 1 whole into sin square beta, that is the value of sin square n beta divided by sin square beta. So that value of sin square n beta by sin square beta is putted in the equation of intensity. So we have therefore I is equal to I naught sin square alpha by alpha square into, in place of sin square n beta by sin square beta we use the value, that is n square divided by 1 plus n square minus 1 sin square beta, which is equal to 1 divided by 1 plus n square minus 1 sin square beta into I naught n square sin square alpha by alpha square, the value of I, or I is equal to 1 divided by 1 plus n square minus 1 sin square beta into that particular term is the intensity of a principal maxima, as you obtain I is equal to I naught n square sin square alpha by alpha square, the intensity of principal maxima, intensity of principal maxima, intensity of principal maxima. So the intensity of secondary maximum is obtained from that of expression. If greater the value of n, weaker are the secondary maxima. In other words, we can say as n increases, the intensity of secondary maximum decreases and they become approximately insignificant. Let we prefer a diffraction pattern. Let we draw a diffraction pattern when there are n number of for particular value of n, for n is equal to 3. The diffraction pattern we see so the diffraction pattern for n is equal to 3, we have the pattern like this: maximum, that with the relative intensity here in this axis, here n is equal to 3, here we have relative intensity, again that be theta. Next for n is equal to 4, n is equal to 5, intensity distribution taking as theta, here relative intensity, y axis, we have the diffraction pattern like this. So with the help of this video lecture, we understand Fraunhofer diffraction at n number of slits. We can say that is the multiplicity slits. Same mathematical procedure we adopt as we apply in case of Fraunhofer diffraction at single slit and Fraunhofer diffraction at double slit. resultant amplitude. So, the resultant intensity is calculated by this formula. The resultant intensity, from that expression, that term gives rise to diffraction, this term gives rise to interference. From that particular expression, we can easily calculate the intensity distribution for single slit and double slit. Next, for principal maxima condition, mathematically we show it. That term is indeterminate. So, we can evaluate that term by using limiting condition. Taking limiting condition, you evaluate that value plus minus n. Putting that value in the expression for intensity, we have the condition for principal maximum. That is the condition for principal maximum. Then for minima, I will be minimum when it is satisfy that condition. We clarify it. What will be the number of principal maxima or minima in between two successive principal maxima and minima. Next, condition for secondary maximum is evaluated by taking di by d beta is equal to 0. To achieve that term, we have to use this triangle. Putting these values, we simplify it, and finally, the expression for intensity is equal to that term into intensity of principal maxima. So, in this way, intensity of secondary maximum is evaluated. So, a significant figure regarding the diffraction pattern when there are n is equal to 3 number of slits, when n is equal to 5 means 5 number of slits. These are the diffraction pattern we observe on the screen. So, with this useful and informative notes, let me wind up this session. Thank you.